Cool. So we can start with our first talk, our keynote. I would like to welcome Janakiram. He will be talking about MLOps, extending DevOps to machine learning. So please welcome Janakiram on the stage.
A very good morning to all of you. It's my pleasure to be a part of the DevOps Days India conference. And it's so exciting to see in-person events coming back with a bang. Gives me an opportunity to come back to Bangalore and participate in these huge, massive developer events. This is just the beginning, and I'm hoping to see many more events coming up in the next year and so. So my name is Janakiram. I'm an independent analyst, independent consultant. Been in the industry for 20 plus years. Worked at Microsoft, AWS, and for the last decade I have been a one-man shop. Exactly a decade ago, I was running a DevOps consulting company. Right after my full-time job at AWS, I started a startup, a small company, focusing on migrating businesses to the cloud. This was exactly a decade ago. And since then, DevOps has matured, and today it has become a very stable, very well-defined, and a very mature practice, which has redefined the way operations are done. So what's next for DevOps? What is going to keep us busy, and where is the next wave coming from? So as we can see, machine learning and AI are the next big jargons, buzzwords, and the wave that is taking place in the industry. Just like everything, the ML and AI momentum is also impacting operations. So when you bring the best of DevOps to managing and operationalizing ML systems, what you have is called as MLOps. So today I'm going to talk to you about what is MLOps and what does it mean to a typical DevOps professional. So these are the objectives. I'm going to introduce you to the life cycle of machine learning models. We'll take a closer look at building versus serving the models, and then the rise of MLOps. And because most of us are familiar with DevOps, I'm going to compare and contrast MLOps with DevOps and understand where the differences are and how DevOps gets extended to MLOps. And then we're going to take a closer look at the life cycle and discuss some of the tools and the personas involved in MLOps. Finally, I have an interesting discussion around software engineering versus ML engineering. So this is a very interesting theme, and I thought I will briefly touch upon that. So before I go any further, I want to take a quick poll. How many of you are involved in either building machine learning models or deploying and managing machine learning models? 3, 4. Okay. How many of you are familiar with ML and think that is the next big thing? Okay. Even though I don't see all the hands, trust me, that is the next big thing. You got to be familiar with machine learning. Just like a DevOps engineer has to be familiar with software engineering and how code is written, it is going to be very important for you to understand how machine learning systems work when you move from traditional DevOps to MLOps. So that's a very important aspect. So machine learning is a technique where you take historical data and apply that to an algorithm to arrive at what is called as a model. So a model is an algorithm that is trained and tweaked based on historical data. And this model can be used to perform predictions on unknown, unseen production data. So basically you take large data sets, you bring an algorithm, and you run this algorithm across these data points of a huge data set, and then after you start to evaluate how effective the model is, you lock the model, which is the combination of algorithm plus data, and then you move that into production to perform predictions, classification, and object detection, and so on. So this is the high-level workflow involved in machine learning. So take historical data, split that into a training data set and a test data set, pick an algorithm and apply the algorithm to the training data, and you arrive at what is called as a model, and you test the model by passing the test data and see how accurate the predictions are. And as soon as the accuracy comes to a point where it is acceptable, you freeze the combination of algorithm plus certain parameters that are modified or customized for the data, and you call that as the model, and that model is deployed for performing further predictions. So this is how machine learning typically works, whether it is classical machine learning or more advanced deep learning and some of the recent trends like generative neural networks. Essentially, this is the mechanism through which machine learning models are leveraged. So once the model is available, which is the frozen algorithm with certain parameters customized for the data, it is an artifact. It is like a binary. It is like a DLL or a jar file or a Docker image. And you deploy that and start performing predictions over it. So this is the typical process. Now at a very high level, this can be split into two parts. Typically, machine learning has two lives. One life is the model building part. The other life is the model serving part. The model building part can be compared to the development of software, and model serving can be compared to the deployment of the software. So the model building part is typically done by data scientists and ML researchers and ML engineers who are constantly training the algorithm based on the historical data. And once they are convinced and satisfied with the outcome, they give the model to the operations team and they operationalize and take the model to the production. Sounds very similar to how software is being developed, deployed, and managed. Not very different. So, what is important here is to understand the key difference between model building and model serving. So, model building is all about experimentation and iteration. The best way to look at machine learning is the machine learning building and training is a lot like a science experiment without a formula, right? So when we are creating a new compound in chemistry, or when you are creating a new chemical that doesn't exist in the periodic table, for example, and you are trying to discover something new, you are trying various permutations and combinations of multiple other compounds, and a specific combination of these compounds will yield to a new chemical, a new compound. And that is the moment where you have actually discovered a new compound, right, by combining certain existing things. And what matters the most is what is the amount of those compounds that you are mixing, and that becomes the formula. And that formula can be repeated and replicated to create this new compound multiple times. So in a lot of ways, building a machine learning model is like a science experiment where you are iterating and experimenting till you are convinced with the predictions and how close they are. So it's a lot of iterative process. But once the model is evolved, then it is deployed and managed like any other artifact. So what are the characteristics and what is the difference between building and serving ML models? So as I mentioned, building models is a highly iterative process. ML researchers and ML engineers do this for hours, days, weeks, and sometimes even months, because it depends on how large the data is. So obviously, these algorithms are very mathematically intensive and very computational intensive tasks. So they need very, very powerful infrastructure in terms of CPUs and GPUs. So training machine learning models is a very compute intensive task. And each iteration, which is technically called as an epoch, each iteration of this training goes through a very complex computation process. And to accelerate this, there are certain specialized chips which are typically the GPUs and TPUs and FPGAs that are optimized for performing the training process. So companies like NVIDIA, Intel, AMD, Qualcomm, Google, they're all investing in specialized chips that are not general purpose, but they are purpose built to accelerate the training part of it. So the goal of training is high throughput, where you are accelerating the process of matching the algorithm with the data and freezing the model. Now, once the model is fully trained, it is deployed in the cloud, the data center, or at the edge. Now, edge is a very interesting use case where, for example, you want to find out if every attendee entering the conference room is wearing a mask or not. So you put a camera at the entrance and everyone will pass through the camera, and if someone is not wearing the mask, the camera will draw a red bounding box, will beep, and it will blink. So to perform that, you need to deploy the mask detection model very close to the camera, and it has to do it almost in real time as people enter. So that is actually called as inference. So inference is moving the trained model to production and passing data through that model to detect or to predict what the expected outcome is. And obviously the goal here is reduced latency. Now you cannot have a person walk in all the way and then the camera detecting that he is not wearing the mask. That is a very high latency. So the goal for training is high throughput because we want to accelerate and speed up the training process. The goal for inference, which is applying the model to data, the goal there is reduced latency. So those two are the goals when models are trained and models are deployed for inference. Now obviously, in a typical enterprise that is focused on machine learning and data science, you have pretty large teams and very diverse skill set and talent working towards operationalizing machine learning. So similar to how developers and operational professionals work together to create the DevOps culture, tools and processes, we need to have the data scientists who are focused on data, ML engineers who are building the ML models, and the ops professionals come together to run this entire new discipline of training ML models and deploying ML models, and that's what is called as MLOps. So MLOps is a methodology to unify machine learning development and machine learning operations. Obviously, just like a software engineer doesn't understand the terminology of load balancers, ingress, TLS certificates, auto scaling, and horizontal scale, vertical scale, a machine learning researcher or a machine learning engineer cannot understand what it takes to deploy and how to manage it. That's not his focus. His focus is, how do I identify the right algorithm? How do I pre-process the data? How do I make sure the model is highly accurate and precise? Now, those are the things that keep him busy, keep him engaged all the time. Now, once the model is trained and given to the operations team, they don't worry about what algorithm was used to train the model, what framework was used, which language was used. They only take the artifact, they deploy it in, for example, Kubernetes, and they start to scale, monitor, manage, upgrade, and run it like any other piece of software. So there is a very clear distinction between the ML systems building and the ML systems operations. They are two different job functions altogether. Just like DevOps, this advocates formalizing and automating critical steps of machine learning engineering. It defines a standard set of processes, capabilities, and tools for building, deploying, operationalizing, and managing machine learning systems. In a lot of ways, this is DevOps, but for ML. I'm going to talk more about the differences between typical software engineering and ML systems engineering, but For a practical purpose, you can think of MLOps as DevOps for machine learning, where the science of developing software is different, and the focus is not about developing software, but here it is all about building ML systems. And just like DevOps, MLOps also focuses on repeatability, consistency, scalability, and security. What worked in a ML researcher system on his development machine should work similarly in a highly scalable cloud environment. They shouldn't start from the beginning, from the scratch. So how do I do something small on my laptop and then take it over to a public cloud and run it with a larger data set and a massive infrastructure? For that, I need consistency, repeatability, and highly predictive environment. So as an MLOps engineer, your job is to make sure that you are enabling and empowering ML researchers, data scientists, and ML engineers to get this repeatable, consistent infrastructure for both building the ML models and operationalizing the ML models. Now, that is the job of an ML ops engineer. You need to empower the ML engineers, data scientists, and researchers in getting a consistent, predictable, reliable infrastructure to run their experiments and deploy their models. So that is the fundamental goal of an ML ops professional. So, this diagram looks very familiar. 3/4 of this has been like a standard blueprint for DevOps. We have been seeing this for almost a decade. Now, what happens if you bring ML to the typical DevOps blueprint? The new circle actually has two parts to it. One is model, the other one is data. And software engineering is not going anyway. We still need to code, plan, build, and test. That is our plan, code, build, and test. That is not going away. But to that, we are adding two new disciplines, which is the data science and the model operations. So when you bring this to DevOps, what you have is MLOps. So let's take a closer look at these two in terms of terminology. Trust me, a decade ago, my boss asked me, how do you define DevOps? And it was a very difficult question to answer. This was a decade ago. There was no standard definition for DevOps. Was it automation? Was it provisioning? Was it configuration? Was it change management? Was it scaling? Was it monitoring? Was it testing? We don't know. DevOps was very confusing when it got introduced. And then we had a variety of tools: Chef, Puppet, Ansible, SaltStack, CloudFormation, Cloud Deployment Manager, a lot of tools. And it was very difficult for someone to define what exactly is DevOps. But over a period of time, I think in the last 5-6 years, DevOps has become very mature and the definition has evolved. And today, we don't really think twice before answering the question, what is DevOps? To put it simply, DevOps is continuous integration, continuous deployment, and continuous monitoring. If you bring all these three, and maybe continuous testing to the mix, if you bring all those 3 or 4 disciplines into a culture, what you have is DevOps. Continuous integration, we have mastered it. You commit the code to GitHub and it kicks off a continuous integration process. And the end of that continuous integration process is basically a Docker or an OCI container image that is stored in an OCI registry. Continuous integration part is over. Continuous deployment is take that artifact, package it as a Helm chart or a customize or a Kubernetes YAML, and you basically put that in a GitOps mechanism, and you use Argo CD or Flux, and continuous deployment is mastered. It is done. And once the artifact is deployed, you have the Prometheus, the Loki, and other components running in the Kubernetes observability stack, which are streaming the metrics, events, alerts, and logs to a Grafana dashboard or a Kibana dashboard, and you are monitoring. So continuous integration, continuous deployment, continuous monitoring, all of them are in place, and you as a DevOps professional will own one part of this, very easy to define. Now coming to MLOps, the bottom four or the bottom three won't change. We are still dealing with continuous integration, continuous deployment and monitoring, but above that we have data. Actually this bullet also needs to be a subset of model. Yeah. So in MLOps it all starts with data. Data acquisition or data ingestion, data processing, feature engineering. Then we have the model where you have experimentation, hyperparameter tuning, training and evaluation. And then kicks in continuous integration, deployment and monitoring. And there is an additional continuous process for training. So when you bring all of these into a new job function and a cultural aspect, what you have is MLOps. So in a lot of sense, DevOps plus data and model is equal to MLOps. And MLOps minus data and model is plain vanilla DevOps, as straightforward as that. There is a lot of heavy lifting and a significant work that goes into data operations and model operations. You cannot discount that. It's a very, very intense and critical aspect of MLOps. So we'll take a closer look at that. So if that is the terminology, who are the personas involved in MLOps? Again, let's take a look at the top contributors to DevOps. At a high level, it's a no-brainer. Developers and operators. Developers write code, commit code. Operators build images, deploy images, and monitor and maintain the artifacts, the deployments. In MLOps, apart from developers and operators, we have two more new personas. Data scientists, whose job is to acquire data, ingest data, cleanse data, pre-process data, perform feature engineering, and get the data to a point that is useful for ML researchers and ML engineers to train models. While data is very important for machine learning, it cannot consume data the way it is available. There is a lot of work, heavy lifting that gets done between getting the raw data and the data that is used as input for training. And that part is handled by data scientists. And they do a lot of heavy lifting. Just like garbage in, garbage out, garbage data in, garbage data out, right? So the model is only as effective as the quality of data. If you train a model with garbage data, you only get a garbage model. So data scientists are very, very crucial for the success of MLOps. They take data, they cleanse it, they pre-process it, they feature engineer, they create a feature store and hand it off to the ML researchers who will take over from there and train the model. Their job is to choose the right algorithm and apply the cleansed, pre-processed, clean data, quality data to the algorithm and generate the model. And this model is integrated with rest of the applications by developers. Developers are still very important. For example, if you use Shazam, right, or if you are using a translation application, the user experience matters so much. Now, behind that beautiful user experience in your mobile phone or your web application, there is a lot of code which a software engineer has developed. But that code is interacting with a machine learning model to perform translation or image recognition or anything of that kind. For example, when you pull out your iPhone and use Face ID, there is a lot of software engineering, there is a lot of ML engineering that work behind the scenes. So everyone is equally important to make this work, to make this successful. So this is going to be a very important job function, a cultural shift, a new process, and almost a new set of tools. And when you bring all of them together, what we have is an MLOps culture, MLOps discipline. Now, sorry if this is not visible to the folks sitting in the last row, but this is the ML pipeline, just like a DevOps pipeline. DevOps pipeline has fewer stages, but an ML pipeline has a lot of stages. And every stage is important. But what is unique between DevOps or with DevOps when compared with MLOps is, DevOps is a very mature methodology. Today, if I ask you, how do you want to package your container image? There are well-defined tools for that. You may use Docker BuildX, you may use Builda, you may use Scaffold, right? So, or a simple Docker file with Docker CLI. There are a lot of standardized tools, right? And if I ask you to create a parameterized deployment for Kubernetes, you will create a Helm chart, standardized, right? And you want to perform image scanning, use SNCC. So there is a lot of maturity in DevOps. But trust me, 10 years ago, this was not the case. For everything, there were a dozen tools, and everything overlapped with each other. It was so difficult to define the DevOps pipeline with best of the breed open source and commercial tools. Interestingly, MLOps is where DevOps was 10 years ago. So we are now struggling with a highly fragmented set of tools, both open source and commercial and cloud-based, and it is very, very difficult to handpick best of the breed tools to stitch the MLOps pipeline. So I want to give you a sneak peek of what these tools are and what role they play. So the first thing is data acquisition. So data acquisition is how you acquire or ingest data from external systems. For example, there are cameras, there are mic arrays, there are sensors. Now, these sensors emit telemetry data. Now, that telemetry data has to be ingested into a data processing pipeline. So, how is that done? Kafka, RabbitMQ, and MQTT, right? These are just a tiny subset of the available tools. By no means this is the most comprehensive set of tools, but these are some of the popular tools to ingest data. Now, if someone is using public cloud, they might use Amazon Kinesis on AWS, Event Hub on Azure, Cloud PubSub on Google Cloud. What are they meant for? They are meant for ingesting data coming from sensors and various data sources. So once data is acquired in its raw form, it needs to be processed. Processed is where you drop certain data points or columns and you take an average or you compute, you basically make the data more useful. So for that, depending on the scale, depending on how large the data sets are, we can use pandas, which is very popular among Python developers. We can use a lot of Apache tools. Again, this is just a subset: Apache Spark, Apache Flink, Apache Beam. Now, all of them support data pre-processing. As data comes in, you want to apply computation and perform certain processing on that. These are some of the tools. On the public cloud, there are tools like Amazon Glue. Of course, on Amazon, there are a dozen such tools. You can use Athena, you can use the data, various data tools, but Glue is just one of the examples on AWS. Then Stream Analytics on Azure, the icon that you see there, and Google Dataflow, which is a commercial implementation of Apache Beam. Now, all of these tools perform data pre-processing and they perform cleansing of data so that the raw data becomes more useful. And once the data becomes useful, then you have to identify the features. So feature engineering, I don't want to go into the details, but is a very, very important, very critical stage in the MLOps pipeline. So here, you identify what attributes, what features of data will influence the quality and the accuracy of the model. And that is a science by itself. So to perform feature engineering and to store those features, data scientists use something like TS-Fresh, feature tools, and even pandas, depending on the size of the data. If it is a small Excel file or a CSV file or a TSV file, you can always use pandas, but depending on the scale, you'll use one of those. And then, there is something called Feast, which is a part of the open source Kubeflow stack, and that is Feast, the blue icon that you see there. Tekton is a commercial implementation of Feast, and Amazon SageMaker feature store is one of the commercially available cloud-based ones. Vertex AI from Google has a lot of feature engineering and a feature store. So this is where the data pipe ends. Raw data comes in, it gets ingested, it gets pre-processed, it gets cleansed, it gets wrangled, it gets into feature engineering, and now all the features are identified and ready for the ML researchers and ML engineers to start training the model on the data. So next comes in experimentation and hyperparameter tuning. Remember, I was giving you an example of a chemistry lab exercise, right? You're trying to find a new compound by mixing and matching various chemicals. Now, if you add a little, 2 more ounces of a chemical, the formula changes. The chemical becomes something else. So you have to be very, very precise in the way you are mixing and matching these chemicals in the exact quality and quantity so that you get a new compound. So very similar to that, we need to perform experimentation and hyperparameter tuning. This is very similar to a chemistry lab exercise. So to perform that, we have a variety of tools, MLflow from Databricks, an open source tool, Kubeflow, one of my favorites and very powerful Kubernetes-based ML platform, Weights and Biases, SageMaker, Vertex AI, Azure ML, Neptune, Katib. Katib is again very well integrated with Kubeflow, ClearML. Now all of them are basically meant for experimentation and saving every experiment, because after you have performed 100 experiments, you realize somewhere in the 99th or 98th iteration, you got better results and you want to go back and tune that. So to perform that, all the history of your experimentation will have to be saved, and you should go back and look at the results. So where do you store, how do you store, how do you maintain the state of all these experiments? Well, these tools take care of that. So for example, MLflow has a very nice dashboard where you can search for your previous experiments and choose one of the iterations in your experiment and fine tune on that. So this is about experimentation. And once you do experimentation and basic hyperparameter tuning, you want to now do it at scale, and that's where you start actually training the model. You basically pick up TensorFlow, PyTorch, MXNet. If you are on Windows, you'll choose MLNet, H2O, Scikit-learn, one of those machine learning frameworks and runtimes, and you now actually start to train this with a much more scalable infrastructure, maybe in the cloud with NVIDIA GPUs, or maybe in Google Cloud with TPUs, it depends. But if you see, there is a perception that if you master TensorFlow, you are an ML specialist. No, TensorFlow figures only on this slide. It's only meant for training. Before and after TensorFlow, there are dozens of tools. So what I want to emphasize is, machine learning is not just about training or mastering TensorFlow and PyTorch. No, it is only 20%. The remaining 80% is a variety of tools, variety of processes, and a very different culture to operationalize, productionize, and to see value out of ML. So once the training is done, then there comes in making sure that the models don't have bias, and you can explain why AI has made a decision. And I want to give you an example. Today, when you apply for a loan, it could be an education loan, a personal loan, or a home loan at a bank, and it gets denied, it gets rejected. You can go back to the manager and ask him, why did my application get rejected or denied? You have every right. And the manager is expected to sit with you and help you understand why your application was rejected. He would say, look, the collateral that you gave doesn't match the value of the loan you're applying. So we are not able to process this application because the amount of loan that you are taking is far more higher than the value of the assets that you are giving to us. Fair enough. Then you will negotiate, you will take a smaller amount as loan, or you will include another property of yours as a collateral and you get the same amount as loan. That's the next step. But what is most important is the bank is able to justify and put a reason on why your loan application is rejected in a very explainable form. Now, fast forward to 2025, where every bank will use artificial intelligence to approve or reject a loan, right? Now, same thing happens. AI has rejected your loan. No human was involved in this decision. And you as the applicant go back to the bank and ask, why was my loan application rejected? Now, who is responsible? The manager or the bank cannot say, I didn't make the decision, it's the AI that did the decision. If AI did the decision, what factors influenced AI to reject the application? Today, this is one of the biggest challenges. AI is not transparent enough, AI is not explainable enough, AI is not interpretable enough to help us understand why a specific decision is made. And the biggest worry is, because of all the noise, the AI model can get biased. The AI model can get biased with a lot of factors. There are a lot of examples on Twitter on how bots were taken down. Microsoft launched a bot on Twitter and it was taken down in 48 hours because the bot that got trained on Twitter's own data started abusing people. Right? And it started really, it started to use very violent conversations with the Twitter users, and Microsoft had to take down that bot because it was causing a lot of damage. Why was that the case? Because the AI bot that was deployed had a lot of bias. And it was very difficult to explain why that bot was behaving like that. So the most important aspect of AI today is explainability, unbiased fairness, and interpretability. Before an ML model gets into production, someone will have to do the sanity check to make sure the AI model is explainable. And there is a standard that is evolving. Why an AI model made a decision that way? It should be able to explain. That is the most important step. And all the popular frameworks, like Sharp is an open source tool, Fiddler is another tool, Aporia is a company that focuses on explainability, and SageMaker has something called Clarify, and Vertex AI has Responsible AI. Azure ML is also focused on this. So this is becoming very important. And a human in the loop, someone who understands this as an important aspect, will approve the model after making sure there is no bias. It is like in the software engineering, in our typical CI/CD pipeline, you do a PR in GitOps, and before someone approves that PR, they actually test it, and only if they are convinced they will merge. So it's very similar to that. Here there is no PR, but someone will manually stop the MLOps pipeline and make sure there is no bias, and then move to the next one. Model packaging and deployment. And this is where we get to see most familiar technologies. And what is interesting is in this entire pipeline, this is the first time we are seeing Docker and Kubernetes. Right? So model packaging and deployment, again, it is all about OCI. It's all about Docker. It is all about Kubernetes. You take the model, you create a Docker file wrapping it, you turn that into a pod, you deploy it. So it's a standard CD process. And SageMaker, Vertex AI, Azure ML, all of them heavily leverage Kubernetes for deploying and serving ML models. So finally, for model serving, it's not always a good idea to package your model in a Docker image. Why? Because each model, depending on what it does, can run into few gigabytes. Now, in a microservices pattern, it's not a good idea to package one artifact of 4 GB inside one Docker file. Not a good idea. That is first thing. Second thing is, if you are running this model on GPU, that single model will consume the entire GPU. Now, models cannot be concurrently run on one GPU. One model to one GPU, and GPUs are very expensive. So you cannot really have multiple models deployed on a single GPU machine. And that is the problem if you are packaging your model as a Docker file and translating that into a pod and running it on Kubernetes. You cannot do anything else on that cluster. So what is the solution? Well, you don't package your model as a container, but you bring a model server in between the models and the consumers of the model. And that's where you have MLflow, Kserve, NVIDIA's Triton Inference Server, Seldon Core, and of course the cloud-based ones. What they do is very interesting. You don't package your model into a Docker image or an OCI image. You put all the models in object storage, maybe Amazon S3, Google Cloud Storage, or even MinIO. And then you deploy Kserve or NVIDIA Triton Inference Server, and you point the model server to the object storage bucket so that it loads the model when and where required, and it can multitask. Just like an OS manages multiple cores of the CPU, the model server can handle multiple cores of the GPU while loading and unloading models on the fly. It's almost like the OS for the GPU. And behind the scenes, they all take advantage of NVIDIA CUDA and other technologies. So that is model serving. Finally, deploying and serving the model is not enough. You need to maintain, you need to monitor it. Observability is very critical pillars, right? And again, we see a familiar icon there. What is that? Prometheus. So Prometheus is still very relevant for model monitoring. But apart from that, you have a lot of other tools which are highly focused on model monitoring and not generic metrics. Because the way Prometheus works is, it's a generic agent that can scrap any metrics and upload it to a tool like Grafana. But we need to get much more detailed metadata out of model inferencing. So these are the tools like Aporia, Neptune, Arise. They all master in model-based observability, not generic observability delivered by Prometheus. Prometheus is a very generic monitoring agent. So now going back to this slide and talking to you about that, so this is where we were. So I covered all these phases and I talked about the popular tools for each of those. Now this is the MLOps pipeline, which is much more broader and much more comprehensive than a typical DevOps pipeline. Finally, I want to wrap up my discussion with this slide. I'm extremely sorry for the font size. I had to bring a lot of data into it. So how do you compare software engineering with ML systems engineering? I will share this slide. You can refer it back. But language, software engineering can be written, or software can be written in any language, from assembly to the most recent Rust. Whereas machine learning is typically confined to Python or Julia and sometimes Java. But it's fairly limited set of languages. The integrated development environment, you can use anywhere from Vim to JetBrains, VS Code, whatever. But the most popular IDE for ML is Jupyter Notebook. Of course, you can use the tools like Spider and JetBrains IDE and so on, but majority of the data scientists and ML engineers prefer Jupyter Notebook. For SCM, it is Git, whether it is ML or typical software. For optimization target, we target an x86 CPU or an ARM64 CPU, whereas when you are targeting ML, you also worry about GPU. You accelerate your model, you optimize your model for GPU. The compiled unit in software engineering is a binary. It's a DLL or an EXE or any of the executable that is packaged, that is directly executable. Now, in terms of ML systems, the data folks will deliver a data set, a cleansed data set, pre-processed data set. The ML engineers will deliver a model. So that is the compiled unit, which is the outcome of the effort. Now for testing, we typically do unit test, functional test, and usability test. In the ML environment, the test for data pipeline is data quality, and the bias, fairness, interpretability, explainability is what is important in ML systems. That is the testing that needs to be done, mostly manual. The artifact that is generated out of software engineering is a container image, an OCI image. In ML systems, it's a new data set or a graph, a TensorFlow graph, PyTorch graph, or an Onyx graph, or even a container image if the image is small. Artifact storage is registry, something like Harbor, something like Docker Hub, something like the OCI registry, anything. Whereas for ML systems, it is a data lake, a data warehouse, a relational data store, anything, but it's a data store. And the models are stored in object registry, object storage, which is like S3 or MinIO. And then there is something called model registry, where you register all the models, and typically that is an enhanced object storage with some metadata. Deployment and runtime, Kubernetes, hands down. For deployment and runtime of ML systems, it's a model server like Kserve, Seldon, Triton, and so on. And you may want to deploy directly on Kubernetes if the size of the model artifact is small. Like I said, you can package it as an image and deploy it on Kubernetes. Observability focuses primarily on availability, reliability, and throughput. Those are the metrics that an SRE will be measured on. Same metrics are applicable for observability of ML systems, but there is one important aspect called drift. What is drift? So drift is basically the difference between the data that was used for training and the data that is being used for inference. That means, just like a developer says, it works on my machine, the ML engineer will say, oh, on my machine, I get 95% accuracy, but in production, it's only 60% accurate. And what happens is the data, the inference quality degrades over a period of time. Initially, it might be very high, but as the data varies from the original format to other formats, there will be a difference between the accuracy and precision of the ML model, and that is called the drift. When the drift happens, it's an indication that you got to retrain the model and deploy it back. So that brings us to the last one. Now, what is the CI/CD trigger in software engineering? A Git commit, right? In GitOps, you do a Git commit and it kicks off the entire pipeline. Now, in ML systems, what kicks off the continuous training pipeline? It is the drift detection. When observability reports that the accuracy of the model is dropping beyond a specific acceptable threshold, it is going to kick off training all over again, and our MLOps pipeline will be executed again. So Git commit is the trigger for CI/CD in software engineering, and drift detection is the trigger for continuous training pipeline. And that comes to the end of this session. I hope you found this useful. I am around for Q&A.
Morning, Janakiram sir. First of all, thank you for the great talk. Yashwardhan, I'm in the field of SRE. I'm not much into ML, but like I've played with it for a few months. So one thought used to nag me a lot that when we are training models at scale, right, we are dealing with a massive amount of data. For example, there can be millions of data points, which makes the training process very data as well as time consuming, right? So when you're training such models, I read about checkpointing, but I could not exactly understand. Like there are multiple sources which sounded like that it was a responsibility of MLOps engineers. Somewhere it felt like it was the responsibility of developers. So I just wanted to know your thoughts that on the basis of your experience of advising so many other companies around MLOps, like Is it still challenging? Is that problem of checkpointing sorted out? Is it still a responsibility of developers, or like it's totally under the scope of MLOps? That's all what I wanted to know.
Yeah, so checkpointing is basically, it's like putting a breakpoint in your code execution in your IDE, right? So similarly, when you are training an ML model and you are basically arrived at a point, it looks like this is the combination you want to settle for, you do a checkpoint there. And what it basically does is it will skip the remaining iterations and it will create a model exactly at that point where you call back for checkpoint. It's almost like a breakpoint that you manually insert in an IDE and stop the execution and debug from there. So a checkpoint is very similar in the training process where you halt the remaining iterations because you have arrived at a point which seems to be what you wanted to get out of. So it's more like a practice that most of the ML engineers will use, and it is very specific to that persona. It is not left to production or it is not left to anyone else. It is the job of the ML engineer or researcher who is basically training the model and experimenting with that.
All right, thank you, sir. That answers my question.
Cool.
Janakiram, Vishal here. Great talk, learned a lot. One question I have is, when you look at DevOps, the barrier to entry was relatively low. You could bring up an entire stack on your machine and get going, right? With MLOps, there is data, there is a lot of compute, maybe you need like 10, 20 machines, right? So do you think that will affect how open source becomes more prevalent or doesn't in MLOps space?
Absolutely. So great question. So currently the MLOps landscape is a jungle. It's the most fragmented, most cluttered, most confusing landscape. For doing one thing, you get 24 tools, and most of them are open source. So, my understanding is, in about 2 years from now, just like for DevOps, we have handpicked best of the breed tools to stitch our pipeline, there will be the most recommended, proven set of open source tools that fit into each of these stages of the MLOps pipeline. But today, there is no authoritative set of tool chain to do end-to-end MLOps pipeline. But one thing that is very sure is, unlike anything else, ML is built heavily on open source. So, there is no doubt that MLOps phenomenon will be driven by open source tools. It's just that the challenge is there are too many open source tools to do the same thing. But once the dust settles and once we have identified the best of the breed tools, it is all open source that is going to drive this new phenomenon. Cool. So I think we will break for coffee then. So thanks so much for attending. Have a great conference ahead. I'll be around. Thank you.